Hello and welcome to section 2.8 of our linear algebra notes. Today we'll talk about subspaces of Rn, and in particular we'll talk about the column space and null space of a matrix and the definition of a basis and how to find bases for certain subspaces. So a subspace of the vector space Rn is any set H that sits inside Rn and has three properties. It has to contain the zero vector. Sums of elements in that space have to stay within that space, and anytime you take a vector in H and you multiply it by a constant, like a real number, that stays in the space. So our first example will be to prove that the set of all vectors of the form, and let's just write this down in set notation, A0, 0, and here A is a real number, so any real number. We want to prove that this is a subspace of our 3. So for example, like -1, 0, 0 is in this subspace, or is in this set H. Okay, so first we need to show that the 0 vector is in there. Well, if A equals 0, then we get 0, 0, 0, which is the 0 vector, and that's in H. The second bit that we need to prove is if we have two different vectors, let's call them U and V. So we have, here's U, we'll give it A1, and V, we'll let the first entry be A2. Then we want to look at what happens when we add them together. And basically we're trying to show that when we add them together, we still get something that's of that same form where we have a real number in that first row followed by zeros in the second row. And this is in H since A1 plus A2 is a real number. And then finally, when we multiply by a constant, well, that's the same thing as multiplying each entry by that constant. And so we get CA1, 0, 0. And that's again in H, since that C times A1 is a real number times a real number, which is a real number. And sometimes we write a box to represent that we're done with a proof. So this is one of our proof type things, and so we can say, so H is a really I should have said that at the end before I put the box of, in this case we're dealing with R3. So let's put our box there. Okay. So one nice object that is always a subspace is span. So if we have a set of vectors v1 through vk, their span is a subspace. And let's look at that. So if we think about the 0 vector, well, that's 0 times v1 plus 0 times v2 all the way out to 0 times vk. And that is a linear combination of those vectors v1 through vk. So 0 is definitely in the span. And then if we take two vectors in the span, this time I'll use u and w since our vectors, since our set that we're starting with is v's. It doesn't matter what variables we use as long as we use arbitrary elements of that set. So we're not like assigning any values to u and w, we're just using them as variables. And then, when we add them together, we can use some of our properties of vector addition to go ahead and group our coefficients of, or our vectors in our span, our vectors that we're taking the span of together. And so this is by commutativity of our vector addition. And so further, we can use the distributive property to group our coefficients together. And now you can really see, that should be a BK, that this is by the distributive property. And you could cite which theorem number this is in your textbook, or you can write down the name of the property. Either way is fine. I'll do it the other way in the next example. So now this is a linear combination of v1 through vk. So that sum is in fact in, and this little, I've been using this, but this thing means notation there means in the span of this set V1 through Vk. Okay, and then our final step is to look at what happens when we multiply through by a constant. And so we get C times A1 V1 up through C times AK Vk. That we got that again by using the distributive property. And that's already, you can see, each of these coefficients is a real number. So this is a linear combination, again, of our vectors V1 through Vk. So constant times vector is also in the span. And so we have our span is, in fact, a subspace of Rn, which is nice because now anytime you want to show that something is a subspace, if you can show that it's a span of something, then you're done. Speaking of things that are the spans of things that end up being a subspace, we can talk about something called the column space, and then we'll talk about the null space. So the column space is the set of all linear combinations of the columns of A. In other words, it's the set of all B such that there exists some x such that ax equals b for some x. So if you think about this as a linear transformation, it's the range of the transformation t of x equals ax. So in order to determine whether something is in the column space, then all we really care about is it a linear combination of the columns of A? Or in other words, is there an x that we can input, we can multiply by A to get B? Well, that's exactly going through and testing if if we think of it as a system of linear equations, testing whether it's consistent. So we make an augmented matrix, and then we row reduce. So I'll just write that little squiggly line to represent that we have done that row reduction already. And now you see that although we have a row of zeros in the bottom, it's not met with a zero in the right-hand column of the augmented matrix. So it's consistent. And in fact, if you want to write down if you want to write it down explicitly, well, remember that each of these equations is, in fact, a way to write, so x3 equals free. So we could let x3 be anything we want. Let's say, so for example, we could let x3 equal 0, and we could let it be other things. So there's infinitely many options to do that. But if we let it equal 0, then we can write 1, 14, negative 9 as, well, x1 is negative 5. So that means we're doing negative 5 times the first column. x2 will then be 7 since we're letting x3 be 0. So plus 7 times the second column. And then we chose to make our free variable 0, and so we don't even use that third column. There's other ways, but the point is that it's in the column space because it's a linear combination of the columns. And now you can apply the same technique for our first quiz question to test if 7, 0 is in the column space of the given matrix. Okay, so null space is kind of a related thing, but this time instead of looking at the columns of A or the span of the columns, now we're actually looking at inputs. So we're actually looking at what x's can be multiplied by A to get 0. And this is in fact a subspace of Rn, and so this is called the null space. And so the set of all solutions to Ax equals 0 is in fact a subspace. And so let's go ahead and go over that proof. So here, first of all, x equals 0 is in the null space of A. And that's because if you multiply A times 0, the 0 vector, you get back the 0 vector. And what we want is values that give us the 0 vector. The second statement says, well, if u and v are in the null space of A, let's go ahead and write an equation involving u and v, because it's always easier to do proofs with equations. So then we have A times u equals 0 and A times v equals 0. So now let's look at their sum. Well, if we look at A times u plus v, well, first of all, we can use the distributive property, and I promised you that this time I would pull out the actual theorem number. So this is theorem 2b in this chapter. And since both of those are zeros by above, we can substitute, and that's just since u and v are in the null space of A. And then finally, when we add 0 to a vector, by theorem 1c, we get 0 back. And so now what we've shown is A times 0 plus v equals 0. So u plus v, I said 0 plus v, it's A times u plus v is 0. So u plus v is in the null space of A. And finally, we're ready to go to part 3, which is looking at what happens when we multiply u by a constant. And we have a theorem that says we can pull that constant out. That's theorem 2d, and that equals c times 0, since A times u equals 0, because u is in the null space of A. And that, of course, equals 0. So a constant times a vector in the null space gives us something in the null space. So now we know that the null space of any matrix is, in fact, a subspace of, and here we have to be careful, since it's the solutions, it's the input, so it's in R to the number of columns of A. Okay, so now let's talk about a notion of basis. So a basis for a subspace H is any set that's linearly independent. That's something we already know how to do. And then we talk about we need it to span the space itself, H. So not the whole space that it sits inside, not the Rn or Rm, but rather just the subspace itself. And so before we kind of get to that, let's do an example that might be a little more familiar. So the standard basis, E1 through En, remember, it's the columns of the identity matrix, right? So EI is the vector that has an I in the, has a 1 in the ith position and zeros everywhere else. So this is the identity matrix, and it's already in reduced echelon form. So to check linearly independent, we just look for pivots. So in fact, it's pretty clear to see there's a pivot just along each diagonal. So we have a pivot in every column. So certainly these vectors are linearly independent, but in fact we have a pivot in every row, and as of right now, we're looking to span our whole Rn. So in this case, it does, and so these are a basis. Okay, so for your quiz then, you need to test whether these two vectors given here are linearly independent, and if they're not, then you're already done, because if they're not linearly independent, they can't be a basis. But if they span R2, if they are linearly independent, then you need to check to see if they span R2, because you need to have both of those properties in order to be a basis. Okay, so now let's talk about finding a basis for the null space of a matrix. So if we start with a matrix A, and I went ahead and recorded the reduced echelon form of A, and we want to find a basis for the null space. So remember, what we're looking for is vectors that are linearly independent and span the solution set to AX equals 0. So what we can do is we can actually write down this set of equations. So let's see, we have 3 halves x4 equals 0, and then we have x3 plus 5 fourths x4 equals 0. Ooh, I missed x2 because x2 is free, but we do want to go ahead and write it down. Oh, I guess we don't need to just yet. That's when we're finally solving for it. Okay, so if we want to write our solutions, we need to solve for our basic variables in terms of our free variables. So here we have 3x2 minus 3 halves x4. Here's where we needed our x2 equal to itself since it's free. X3 is negative 5/4 x4, and then x4 is free. And if you think about how we wrote vectors in parametric vector form, we pulled out the coefficient of the first variable, and then we pulled out the coefficient of the second free variable. And here's what we got. Well, in fact, to find a basis then, we know these are going to span our solution set because we've just written our solution set as a span of these guys. And they're linearly independent. It's not too hard to check that because basically you have these where the free variables show up as ones, those kind of can't really be eliminated by row operations. So they wind up being pivots if you were to take this and row reduce. And so you're going to have a pivot in every column, which is going to make them linearly independent. And so we just write the vectors, not the span of the vectors, because it's asking us for a basis. So by saying we're talking about a basis, we're actually looking for a set of vectors, and then we're going to take their span to get our space. So you can think of a basis as a building block for our space. Okay, and then for column space, it's actually even easier to do. So to find a basis for the column space of a matrix, what we need to do is just take, if we just think about the pivot columns, you'll notice, let's go. So this first matrix A has columns A1, A2, A3, and A4. And then our reduced echelon form, we have B1, B2, B3, and B4. So what we need to do here is first notice that the places that we have pivots are going to be the most important places. The other columns are actually linear combinations of our basic columns. So B2, for instance, equals -3 times B1, and B4 equals 3/2. That column B4 is 3/2 times B1 plus 5/4 times B3. So we don't really need those two columns in order to get the span of the columns in this reduced echelon form. Well, the original matrix has the same column relationships as the reduced echelon form, right? Because it has the same AX equals 0, has the same solutions as the reduced echelon form of A times X equals 0. So what that means is that we can ignore the columns that have those same relationships. And so a basis for the column space of A is given by just taking the columns in A that correspond to pivots in the reduced echelon form of the matrix. You can come in now.